If you recall, yesterday, we started looking at implicit differentiation. We need to expand our ability to find slope of a tangent line, to find derivatives. And now we're going to move away from just having a function. That's a pretty strong restriction to have y as a function of x all the time. So we have implicit differentiation. This is what we're going to use when x and y are related, but not by a function. This is going to be very different than treating x and y as separate variables. That's another way that x and y can show up in some kind of equation or function, where we're treating them as separate independent variables. But here, x and y are going to be related. They are not independent of each other. So for this, we're going to be using the chain rule. We'll take the derivative with respect to y, and then we'll multiply by the derivative of y with respect to x. And so when we see a term with an x and y in it, we're going to be using the chain rule after we take the derivative with respect to y, but we're going to have to think of y as having a bunch of x in it. So we're going to have to treat it like a product rule along with a chain rule. And in the example we have here, a chain rule with a product rule with some more chain rule because of the implicit differentiation. So remember, if you see x and y as a product or a quotient, we're going to have to use the product rule or the quotient rule. So this, in addition to the chain rule, if x and y are in a product together, we're going to need the product rule. So here's an example. Sine of xy is equal to x. The trick here is, the problem here is that we can't solve for y. We don't have a convenient way to solve for y in this equation. So I suppose we could use sine inverse, but using sine inverse trig functions introduces some problems that restricts our domain and all kinds of other things. So we're going to avoid all that. We're going to avoid this solving for y business, and we're just going to use implicit differentiation. So let's find the equation of the line tangent to sine xy equals x, that's some curve, a relationship between x and y, at the point 1 pi over 2. So the plan is to take the derivative with respect to x of the whole thing, of all the terms. Take the derivative with respect to x of both sides, sine of xy, and the derivative with respect to x of x. On the right side, this will be easy. The derivative with respect to x will just be 1. But on the left, I've got the sine of x times y. So the derivative of sine of something is the cosine of that thing times the derivative of that thing. Now, in that thing, I've got an x and a y combined with a product, and that says we're going to need the product rule. So when x and y are combined in a product, we're going to need the product rule. So the derivative of sine of a thing is cosine of that thing times the derivative of that thing. And the derivative of that thing is going to need a product rule, where our first is an x, and our second function is y. When we say the derivative of y is 1, that's the derivative with respect to y. So we have to multiply by the derivative of y with respect to x. The important thing to note here is that when we write 1, that's the derivative with respect to y. So the chain rule says we have to multiply by the derivative of y with respect to x. So now we're using the product rule for the derivative of the inside. We say the derivative of the first times the second plus the first times the derivative of the second. And the derivative of x with respect to x is just 1. At this point, we could try solving for dy dx. We don't have to. We're going to eventually. We could plug in the points and then solve for dy dx, or we could solve for dy dx as is. If we want to solve for dy dx, notice that dy dx is inside this factor, so we might want to get rid of this cosine of xy. So maybe we'll write y plus x times dy dx is equal to 1 divided by cosine of xy. Then we could subtract y from both sides. And then divide by x. Weird way of looking at it. We could get a common denominator if we want to rewrite this. I don't know if this would be any better, but maybe this is not the stop we want to make. Maybe we have a common factor of x, so a common denominator would require a cosine of xy. So maybe we write this as 1 minus y cosine xy over x cosine xy. I don't know if that's better or. Then if we want the slope of our tangent line, we just evaluate dy dx at the point 1 pi over 2. So we'll have 1 minus y times the cosine of xy, so x is 1 times pi over 2, all divided by x, which is 1 times the cosine of 1 times pi over 2. So what happens here? What has happened? What is the cosine of pi over 2? Hey Siri, what's cosine of pi over 2? Hey Siri, what's the cosine of pi over 2? Oh, Siri's not helpful. All she heard was pi over 2. She's like, well, I don't know trig. So cosine of pi over 2 is equal to 0. So what's happened here? Let's not trust my algebra. If I plug it into this first one up here, I get 1 over x times the cosine of 1. Oops, x is 1. And we've got the same problem down here. Same problem. So we calculated the slope, and the slope is undefined. What does that mean when the slope is undefined? What does it mean when we have a line with an undefined slope? Change in y is 1, change in x is 0. What kind of line does that? Y changes when x doesn't move at all. Y changes when x doesn't move at all. What kind of line are we dealing with? So in this case, the tangent line is vertical, because a line with an undefined slope is a vertical line. So a vertical line has an equation x equals, all that matters is the x. So our tangent line is just x equals 1. Oops, I erased it. Dang it. So we get an excellent graph of this. We're interested at what's going on at 1 and pi over 2. And 1 pi over 2 looks like it's going to be this point right here at this little bump, or maybe this one up here, or maybe this one up here. It looks like we got a lot of these points. And notice that what's happening at 1 is that it looks like we have a vertical line. So it looks like our analysis is correct. When we took the derivative, when we find dy dx, we get an undefined value at this point. Undefined, a line with an undefined slope is a vertical line. So x equals 1 will do. Any questions? We need a variety of graphing calculators because our graphing calculator, the TI-84 one, would not be able to graph this, make an implicit plot. And I don't know if we can do this on Desmos. Does anybody know if we can do implicit plots on Desmos? Nope. So here we can see what that point, a little bit better view of that point. We got a little more grid line going on. So 1 and pi over 2. Pi over 2 is about 1.6. And that's about where these lines intersect. Here's 1, here's 0.5. So somewhere in there at 1.6 is going to be our 1.57. Yeah, there we go. Unfortunately, I guess Desmos does not allow me to click on points for implicitly defined curves, but there it is. Any questions? Comments? Slide remote. Yes. Uh-huh. In order to get rid of which one? Over here? Or in well, we can't cancel the x and y inside the cosine because they're inside the cosine. So what we did was I have x times dy dx. So this y is included by addition, so I subtracted it from both sides. And then this x is being multiplied, so I divided everything by x. And then from here to this last one down here, I just got a common denominator by multiplying the x, the y over x by cosine of xy over cosine of xy. And that gave us a common denominator. So what I did was, we have already an x in common, so I needed on top and bottom just a cosine of xy. Just to get a common denominator, because I thought I might see something else if I looked at this as one fraction rather than the terms, but it didn't make a difference. I also didn't write 1 over cosine as secant in this case because I wouldn't have remembered. Because as soon as I tried to plug in pi over 2, I would have had to think about secant as being 1 over cosine. So I just left it as 1 over cosine. Any questions? In this case, notice that the y only appears one time. So as an alternate, in an alternate reality, we might want to try to solve for y and then write y as a function of x. And the reason why I picked this one is because it'd be messy, but still only with one instance of y, maybe we could do it. So if I sine inverse both sides, already we're starting with the fishy stuff, but that's fine. The reason that we might want to try this is that sine inverse is a derivative that we know. So let's see what happens. If we want to solve for y, then we'll divide by x. So y is going to be sine inverse x divided by x. So in this alternate reality version, I can take the derivative dy dx directly because I've written it as a function. Let's see if it works out to the same thing. Clearly, it's not going to look the same because now I've got sine inverse running around. But let's see what happens. If I take the derivative, I'm going to have to use the quotient rule, where I have the top is sine inverse. So the derivative of the top is 1 over the square root of 1 minus x squared. The bottom is just x, and so the derivative of the bottom is just 1. We don't have to do any implicit differentiation. That's why we're solving for y. We want to write y as a function of x. And so dy dx space. I'll take the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. Yeah, and already we don't like this, but it's fine. But we can see same things are going to happen. Similar things are going to happen. So that first term, I got two terms that are being divided by x squared. I'm going to use a distributive property and divide both by x squared. And so then I'm going to notice that up in here, I wanted this first one anyway. I didn't want to combine. It's fine. It's fine. Thinking about it too much. X divided by x squared is 1 over x. So this first one becomes 1 over x times square root of 1 minus x squared. This second term is just sine inverse x divided by x squared. Now I want to take dy dx and evaluate it when x is equal to 1. We see the same thing happens. This still works out to 0. In fact, it still works out to 1 times 0, right down here. And this still works out to pi over 2 divided by 1. The sine inverse of 1 will be pi over 2, and 1 squared will be 1. So this is still 1 over 0 minus pi over 2. Oops. So that matches with what we had before. We jump over and look at the graph. And we try to graph y equals sine inverse . We can see that part in green. And this is a result of us using, notice that we're only getting that one little bottom part. This is because we did sine inverse, and sine inverse restricts us. So sine has a domain of all real numbers and a range of -1 to 1. But when we invert that, we don't get the sine going all the way up. We only get to invert sine from negative pi over 2 to pi over 2. So that's why we get this limited piece of the domain for the arc sine, for the inverse sine. We don't get the whole picture. In this case, that's fine because 1 and pi over 2 is inside. That agrees with the domain and range of arc sine. But as we see in this graph, there are other points. It gets really bad. The stuff gets kind of jammed up. There are other points that are missing, that are there when we include all of sine and not there when we include the arc sine, when we try to invert that. This is a similar thing that happens when we try to invert a square. We usually write the square root, but there's a plus or minus square root. There's 2. It's just worse with sine because there's infinitely many. Any questions? How's everybody okay? There's too many solutions to invert this. Because when we invert it, let me turn these off. This is getting noisy. When we invert it, we get not a function. So to make this a function, we have to restrict the inputs. So we only look at sine of x between negative pi over 2 to pi over 2. And so our output is going to go from -1 to 1. That's for inverse sine. Any questions? How's everybody okay? Tell about what we can invert when we're undoing things and just being aware of what the liabilities of trying to invert functions that aren't one-to-one, that aren't injected. How's everybody okay? It's the same as like y equals x squared. And the difference between this and square roots. That square root of x only has that positive one. If I want the plus or minus, turn this, keep getting noisier and noisier. If I write x equals y squared, that's the whole thing, right? x equals y squared contains that same information, but with a plus or minus. Any questions? Comment? I like to bring this up because we don't talk about it often. We talk about various different things. We talk about different things in our algebra backgrounds. We have a variety of algebra backgrounds that lead you to this point. And so I'm not sure how much inverse functions we talked about. Any questions? Most important thing is that there are better graphing calculators than the graphing calculator, the TI-84 graphing calculator. Even though its main feature is supposedly graphing, it's like not very good at graphing. Wolfram Alpha is pretty good at graphing unless you want to like zoom in and look at the graph in detail, in which case it's Desmos. But then Wolfram Alpha is very bad at other things. Like if you want to find the reduced or echelon form of a matrix, Wolfram Alpha is terrible at that. The internet is actually very bad at finding the reduced or echelon form of a matrix. So at that point, it's time to bring in the graphing calculator because the TI-84 is very efficient at finding the reduced or echelon form of a matrix. So it's really weird, the names we have for all of our different tools. So once again, I picked an example where since there was only one instance of y, and it was a little bit fishy to use an inverse function, it's possible to do so and still be useful. We do have to be aware that when we try to do this, solve for y, as soon as we try to do the inverse sine of both sides, fishy things are going on. We're restricting what we're looking at. In this case, it didn't matter because of the point that we were interested in. 1 pi over 2 is good, is in the good part of sine inverse. But if I had the point 1 and then what would be the next one? I just add 2 pi, 5 pi over 2, all of a sudden it's not acceptable. How's everybody okay? I can tell you're all stoked. Because you all look like that. So everybody gets up. So here's what I want you to do. This is the important stuff. So I want you to choose a month and a day. I want you to choose a month and a day. The month you're going to encode as a number in the standard way. So January is 1, February is 2, March is 3rd, and so on. Choose a month and a day. Go ahead and write it down. I can't see that far, so I'm not going to be able to see what you write down. My vision is not that good. Even with contacts on, it's awesome. When you get to a certain age, you get one kind of vision that you can correct for. It's like, well, do you want to see things that are far away, or do you want to see things that are close up? I'm like, well, can I have both? And they're like, oh, no. Your eye shape is fucked up at this point. You get to pick one. Has everybody got one? Some of you haven't picked one yet. Oh, wait, sorry. I'm not supposed to read your minds. I didn't say that. Ignore that. Ignore that. Here's what I want you to do. First, step 1. I'm going to do it as an example. July 12th. So as my example, I would take July, which is 7, and multiply by 2. And now I have 14. I'm going to grab a calculator because at one point we're going to be multiplying by 50. That's foreshadowing. At one point we're going to be multiplying by 50. We just multiplied by 2. 7 times 2, 14. Second, step 2. I want you to add 7 to the result. Not 7 because July, just add 7. Don't add the month, add 7. So I'm going to take the 14 plus 7 is 21. Don't add your month, add just the number 7. The only time you use the month is right there. Step 3. Multiply by 50. Step 4, add the day. Whatever you picked for the day, add that to the result. And step 5, subtract 365. And we'll call that your final result. Does everybody have a final result? Double check your math. You can't just make up a number and have it worked out. So I'm going to do this, make sure this is again, my month is 7. So 7 times 2 is 14. 14 plus 7 is 21 times 50 is 1050. Plus the day 12 is 1062 minus 365. Oops, 365. Yeah, okay. Now you can see all these numbers are very important to dates. There are 365 days in a year most of the time. Most of the time. 75% of the time. There are 7 days in a week, and we use that number. And there are 52 weeks in a year. And it used to be not the case anymore, but you get like 50 weeks of work and then you get like 2 weeks of vacation. That used to be a thing where you get like 2 weeks of vacation. In civilized parts of the world, you get way more than just 2 weeks of vacation, but this is America. You got to fucking work. Now work more, right? You know. But there are 52 weeks in a year. And that's typically how we used to split them up. So these are all very relevant to dates. So, does anybody have final results? Anyone want to report their final results? Anyone have one? What you got? 909. Seems pretty current. Anybody have another final result? What you got? 385. I think you missed something there. You need to spring into action to check that number. A result from the chat of 1215. That's a very chilly number. Yes, very chilly number. 994, another result from the chat. I should have written that one in orange. It's a very fall type of number. Anybody else? Only got 4. What you got? 687. That is a much warmer number. You should like, does everybody like 687? You should, because you're not in school at that point. So that's good. That's a nice summary number. Anybody have another number? One more. What you got? 403. All right. So let's take a look at these. Let's start with the one that is closest. This 909. This is very much feeling like very current. This is nearby. I'm glad that you went first, because this is a September number, right? And it feels very current, because isn't today the 24th? What's the oh, we're 2 days ahead. September 24th. So 2 days ago, is that correct? All right. This 385, I'm not sure about this 385. Let's move on. That one's blocking me. Psychically, that's blocking me. You're giving me problems right here. But this 1215, this is a very cool number. It's a very cool number. This is a very wintry number, right? Because this one is speaking to me. Some of you will know it already. December. This one seems like December 30th. Is that correct, chat? Oh, awesome. 994. Now, this one is also a very fall type of number. This is a very fall type of number, but coming up. This one seems coming up soon. This 994 is feeling very orange to me, because I'm getting October and pumpkin spice. When I think about this number, I think, yeah, this is like smack in the middle of pumpkin spice season, because this says to be October, but early in October. I have to do math. Let me think about that one. The 687, I keep distracted by the 687, right? Because this one is a summary number. Is that right? This is a summary number, right? This is a July. This one says to me July. Is that correct? Oh, good. But early in July, right? This feels like an early in July problem. I can almost hear the fireworks going off, but not quite. But not quite. Is this July 2nd? Awesome. And this 403, this one is a very bouncy number. Can you feel it? 403, because it's spring. Spring. It's a number of new growth, because this is April. This is April. And we're kind of happy because we finished paying our taxes, right? Who had 403? 403? April 18th, right? Because we finished paying our taxes April 18th. I spelled 18 wrong. Oh, 994. What is that? It's 1,000 -6. 1,000 -6. So October, this is early in October. Who had 994? That was in the chat, right? That's why it's hard to see, because it's coming through the internet. And I'm too old to like receive signals from the internet. But this is feeling early in October. Is this October? Wait, what did I just say? -6. Is it October 9th? Oh, good. This one is giving me confusing me, because we don't put zeros on our days. We don't put zeros on our days. This one is giving me April. This one is giving me April, but it's not giving me a day. So, do I have magical powers? Or am I just doing some trickery? Clearly, I'm just doing some trickery because I've clearly stated before, I am not allowed to use my magical powers during class. They're like, oh, you can't use magical powers on students. Michael, but I could teach them all calculus in like a day if you just let me mind control them. And I go, no, you can't do that. It's not cool. Michael, I don't care if it's cool, it's super effective. And I go, no, they have to suffer. I go, fine. And then they're like, oh, before you say anything, it doesn't matter that they suffer the other way. They have to suffer in the traditional way. I'm like, well, fine, no mind control, no magical powers, nothing up my sleeves. So the question is this, what am I doing to take these numbers and then turn them into these dates? That's number one. Number two, why does this work? And number three, why does it take me so long to do that? It's because I'm standing up here trying to do arithmetic. I mean, have you stood up here and tried to do arithmetic? No, I think not. It's very difficult when everybody's looking at you and you're just trying to sit there and do arithmetic. You're like, what is 7 times 2? And I'm like standing up here, I'm like, oh, fuck if I know. How am I supposed to know that? And I'm like, well, you have a master's degree in math. It's like, well, yeah, I also have a calculator to do that kind of stuff for me. But during the demonstration, I didn't want to reach down here and grab my calculator just to do whatever it is that I'm doing to go from the number to the date. So that's your job. Number one, what do? Number two, why does it work? Clearly, it's just going to be some kind of mathematical thing. And there has to be nothing interesting going on because it's just a bunch of numbers that we're using, right? There can't be anything interesting going on. And you're like, oh, dude, that's going to ruin the trick. I'm like, oh, it's a math trick, and math was invented to ruin tricks like this. So we don't get fooled. We don't want to get conned by things. You know what I mean? Anytime someone's trying to convince you of something, it's like, oh, isn't that reasonable? Stop. That person is not your friend. They're trying to sell you something. Because they're like, oh, doesn't that seem reasonable? Don't you want to be a reasonable person? You know that that's a lie because humans are not reasonable. Humans are not rational. We don't think rationally. We're just very good at rationalizing and then convincing ourselves that it's rational. So figure out what it is that I'm doing. And then second, show why it works. And then we'll have the mask off version of this trick tomorrow so that you'll be duly let down by math. That's going to do it for today. I will see you all on tomorrow. Figure this out. Everybody have a good day, and thanks for playing.